This is a welcome to all those going to be watching this on YouTube. And according to the analytics, the second biggest audience I have is in Nigeria. So welcome if you're watching from Nigeria. I was going to respond in one of the Nigerian languages until I found out there's over 500 languages spoken in Nigeria. However, I think we better just stick to English. For those who don't know, there's a YouTube channel and where all the previous recordings are held. The playlist is for CPD for structural engineers. That's one playlist. There's another playlist for the Mathcad extracts as well. Okay, and so today's seminar is about vibration of precast pre-stressed concrete floors. And it's really built around one particular paper and a very simplified approximate calculation that you can do to check if your precast pre-stressed floor is likely to suffer from vibration problems. Now, you may see the thing behind me, the orange helter-skelter looking thing is the staircase, the feature staircase in the beehive. And that is a helical staircase cantilevered off cantilevers off the steel frame. So that was just asking for problems in terms of vibration, but happily they've put a lot of effort into the design of that staircase, and it doesn't really vibrate when you walk up and down it, as I do most days. However, it's a pity they didn't spend a little more time on the rest of the building, because as you can see, it's a multi-story steel frame building and it's all open plan. So there are very few partitions and there's very few extra finishes on the building, and there's no ceilings. And so you're looking at a rather raw steel frame supporting precast floors. And yes, it does vibrate when people walk by, and yes, it can get annoying. So let's just jump straight into it. So this is the 15th seminar for structural engineers, 15 already. And this time we're going to look at the Mast method for calculating the minimum natural frequency required for a floor in a normal walking situation or a rhythmic dancing situation. Now, the Mast paper itself does go on to the third category of machine-induced vibration, but we won't go into that today. So just a reminder of the dynamics of buildings. When the natural frequency of a floor system is close to the forcing frequency and the deflection is significant, motion will be perceptible and annoying. So back in the 1980s, when greed was good and hair was big, we were building fast track construction using multi-story steel frames and lightweight composite floors. And there was a concern about the deflection and the vibration of these floors. And we had a little rule of thumb about if you kept the natural frequency of the floor below about above about 4 hertz, it should be okay. Now, the technology has moved on, and the ability to determine what the actual natural frequency is, rather than an approximate calculation based on deflection. And you can do hours and hours of calculations working those things out. But here today, we're going to talk about an approximation, a simple calculation. So the perception of the vibration in the floor is related to the activity of the occupant. So if, like me, you're engaged in quiet work, you may tolerate less vibration than a person performing an active function such as dancing or aerobics. If the floor system dissipates that energy in a very short period of time, the motion is less likely to be perceived as less annoying. As well, the damping characteristics of the system will also affect the acceptability. So if you've got lots of damping, and that comes from your secondary features like your surface finishes, your partitions, and so on, then your annoyance about your vibration can be much less. So where does it come from? There are three main areas, but it can come either directly or indirectly. Directly to the floor by the people or machinery on that floor, or indirectly by the supports to the floor after transmission through the building structure or even through the ground. The three principal sources of vibration in the building are human activity, which is the most common source of annoying vibration that causes a nuisance, especially if you're looking at sensitive equipment and if you're engaged in any motion sensitive activities such as surgery. So hence it's not a good idea to put a dance studio on top of your operating theatre. So designers of buildings featuring gymnasia or dance studios should take extra care to limit those vibrations in the rest of the building. And the second characteristic is vibrating machinery. And a third is from external forces such as traffic and ground level or even underground. And so if you're building over a road or over or near to an underground railway, it will affect your building. So walking across a floor can be problematic in certain environments, particularly for hospitals or quiet offices. And walking at regular pace applies a repeated force to the floor at a frequency of about 1.8 to 2.2 hertz. This repeated force can lead to resonance, building up a response in the floor. However, walking-induced loading consists of multiple frequencies laid on top of each other, so it's not just one. And generally, people are not walking in sync. Now, if people do walk in sync, it's much likely to hit that resonant frequency, particularly if you have no damping. So when assessing the risk of resonance, it's essential to consider these higher excitation frequencies. So the temptation is to jump straight into something like ETAMS and do a finite element analysis on your floor, calculate the natural frequency or the vibrations. But by the time you've loaded up ETAMS and it's checked your license, you can do a very simple calculation, which we'll show in a moment. You need to take into account your secondary structure and your primary structure. So if you have beams supporting beams, then the deflection of the primary beam will also influence the vibration of the secondary beam. So if you've got concrete floor units supporting on solid walls, then vibration is not usually a problem. However, if you've got concrete floor units supported on steel beams, as we have here in the beehive, the deflection of the beam can have a significant effect on the behavior, and this should be included in the computation of the fundamental natural frequency. So there are a number of factors that are known to influence the human perception of vibration. So the type of activity, the time of day when the activity is being undertaken. So nighttime vibrations will be probably more annoying than daytime vibrations. The type of activity where the activity is, the environment where the activity is taking place. The direction also matters, and it's in relation to where you are. So if you're standing, sitting, or sleeping, it makes a difference. How big is your vibration, the amplitude, and what's the frequency of it? Where is it coming from? That's the source, and the level of damping, and the duration. So a short amount of vibration would be less annoying than a continuous vibration or even intermittent vibrations throughout the day. Now, this chart is taken from the Mast paper, and this gives you an indication of the permissible peak vibration levels that humans may find acceptable in different environments. And so if you're in a dance class, you'd be more tolerant than if you're in an operating theatre. So the vibration of the floor is mainly a serviceability issue. So you'll design your floors at the ultimate limit state, but you still need to check the serviceability issues, including deflection and vibration. And it's primarily related to the discomfort of building occupants. So it's not really about life safety. It's just about how nice is the building to use. The other aspect is if you've got sensitive equipment, and this could be in a factory or in a hospital or an operating theatre, for example, sensitive equipment may be damaged by vibration. And if you have sensitive equipment, you need to specify the maximum permissible acceleration. However, the discomfort to humans, being squidgy organic things, can't be directly quantified because the perception and the tolerance will vary from individual to individual, and it's highly dependent on the circumstances. So what's the minimum natural frequency? Well, the human body is most sensitive to frequencies in the 4 to 8 hertz range. Unfortunately, a lot of floors are built as a natural frequency in the 4 to 8 hertz range. Floors with natural frequencies lower than 3 hertz are not recommended because they're subject to rogue jumping. And the rogues usually being students jumping up and down, seeing how lively they can get their floor. Another table taken on the graph taken from the Mast paper. This shows the impact of damping as you head towards the resonant frequency. And damping has a big influence on moving towards the resonant frequency. And the damping you get in your floor system is dependent on the non-structural items, such as the partitions, ceilings, furniture, and so on. The modal damping of a bare structure is around about 1%. But if you add your non-structural elements, this may increase to about 5%. So ceilings and partitions and any sort of mass. The more mass you have, the better in terms of vibration. Footbridges, being lightweight, long span, and relatively bare, have little interconnection with adjacent members. So they have very little damping. And remember those rogue students again, they're the ones who like to jump up and down on bridges to see how excited they can get. If you're designing for rhythmic activity, now that could be jumping, dancing, or aerobics, these activities are characterized by synchronized crowd movement. That is, people moving together in time. And you need to design your floor to the ultimate limit state conditions, but also check the natural frequency. Now, this is I can say it's a rule of thumb from the Steel Construction Institute in the UK. So rather than the old 4 hertz, they're going right up to 8.4 hertz. If you've got a fundamental frequency of at least 8.4 hertz in the vertical direction and 4 hertz in the horizontal direction, then you don't need to bother calculating the resonant effects, and you don't need to evaluate them. However, you can also design the floor to resist the anticipated dynamic loads due to these rhythmic activities, and you consider them to be an imposed load case. So the vertical natural frequency of the floor should be evaluated for the appropriate mode of vibration for an empty structure. Generally, you're looking at the first mode of vibration. So that's usually either a simply supported beam or a continuous beam over the supports. This is the paper written by Robert Mast, and it was published in the PCI journal back in 2001. And he goes into the background, and much of this presentation is taken from his descriptions in here. And so you'll recognize the particular diagrams. He then goes on to describe the calculations for walking and dancing, but also the third category of vibration in mechanical equipment. So it's an approximate method of calculation. And so the limits of frequency are stated as minimum natural frequency of a structural system. And so we look at the permissible peak accelerations, and these depend upon the mass affected by the activity, the environment in which the vibration occurs, the effectiveness of interaction between these connected structural components, and the degree of damping. So much of the vibration theory is derived from the experience with steel and wood floors, and the Steel Construction Institute in the UK have done an awful lot of work on their floors, particularly the composite floors on steel frame buildings. And some of the figures in this presentation have come from there. If you want to know more, go to the SCI website. Usually, floor vibrations are much less of a problem with the stiffer, more massive concrete floors. Now, traditional in situ concrete floors, by their very nature, need to be quite large. However, modern pre-stressed or post-tension concrete floors can actually do long spans with relatively thin slabs. That's where the serviceability issues may arise. So this is the Mathcad calculation. So let's open it up. So here is the Mathcad calculation. It's only 2 pages. And my convention, as usual, is to highlight the inputs in yellow. And then I put the outputs in a kind of shade of orange as well. And the unshaded text are the calculations from the input. And again, the usual convention is you put descriptions on the left, calculations in the middle, and the references on the right. So we're looking at a flow of calculations from left to right and top to bottom. So we give it an input of the floor span, the floor thickness, and the unit weight. And we add a superimposed dead load. Again, you don't need to put too much in there. The more weight you have in your system, the better in terms of vibration. You work out the Young's modulus, in this case from our own NZS 3101, and you put in the live load. Again, you don't put in the full live load, but a proportion of it. So this is a residential building, and we're looking at about half the normal live load to add to the instantaneous deflection. Now, again, it's a little conservative to look at these floors as simply supported, but it's a simple calculation. So behind that is the simple 5W L to the power 4 divided by 384 E and I. Now we've increased the E value because you're looking at an instantaneous deflection. And the quicker you apply the load to any structure, the stiffer it suddenly becomes. And from that instantaneous deflection, we can get the natural frequency of this floor as 5.34 hertz. So we're going to use it for walking, first of all. We take in consideration the whole bay. We take an empirical constant of K taken from table 1 of the Mast paper of 58 kilonewtons and apply an approximate modal damping ratio, in this case 5%. And we get a natural frequency that's required of 4. So is our natural frequency bigger than the required? And happily it is. So we then go on to dancing. I've put the tables in little areas so you can expand or shrink them down as required. So when we're looking at dancing, we take a constant K of 1.3 and carry the acceleration limit from table 2 and the other parameters from table 3. You have a forcing frequency, which is typical with dancing, of 3 hertz. And a dynamic coefficient, again from the table, of 0.05. You take a value of the weight of participants, and again, this is much lower than the normal UDL you would apply for a live loading. And then top that all up, put it into the equation to get your minimum natural frequency required for the dancing situation. And as it turns out, that's 3.38 hertz. Is our natural frequency bigger than that? Yes, then it's okay. For mechanical equipment, I haven't written up the calculation for that, so go see the Mast paper. So finally, the references, our own NZS 3101 for the concrete, and that's the reference for the Mast paper. And if you want to see more about vibrations, go look at the Steel Construction Institute's website at steelconstruction.info. Now, our next seminar will be on structural insulated panels, and there may be several of those because there's quite a lot to talk about on SIPs.